Welcome back. Let's review from last time. The relativistic factor gamma is given by which of these formulas is correct? That's right, it's C. It's a fraction. The denominator has a square root in it, and it's the square root of 1 minus v squared over c squared, where v is the velocity between the stationary frame and the moving frame. And everything we're going to talk about in this chapter is about relative velocities between frames until we get to the very end. You learned last time that moving clocks run. Suppose you see a moving clock go by. Its hands are turning slow or fast. Answer is they turn slow. Okay, we also learned that moving sticks, not that they appear to be or that you believe them to be erroneously, but that they actually are physically measured to be shorter. That's called length contraction. We're going to talk about the Lorentz transformation equations. This is the idea that underlies all of this time dilation and length contraction that we talked about. And real professionals always do it this way. We use the Lorentz transformation to relate two different events together, and then we analyze those times and positions to see what we can learn about the way relativity works. Before we do that, let's review again a little bit. You encountered this in the reading. If a cockroach stows away on a quick trip to the moon and back, it will, which one of these? Best scientific answer. It will live longer than its siblings because it's younger when it gets back. It has moved and its clock has run slow compared to its siblings, and so it's actually younger than its siblings when it gets back. When we see a comet go by on its way to the sun, we measure the comet to be which of these? Yep, it's a little shorter. That's the length contraction. Distant galaxies are observed to be moving away from us at very high speeds, nearly the speed of light. When light from these distant galaxies, from the stars in these distant galaxies, which are going away from us really fast, arrive at us, we see these light waves moving at what speed? Yes, exactly at c. That's the mystery of relativity. The weird fact that light always travels at 3 times 10 to the 8 meters per second means that and the answer is B. Space and time behave strangely. You might think that it would mean that speed doesn't mean what we thought it meant either. You'll think that a little later, but the speed between two frames is the same. It's measured to be the same from both frames. The stationary frame sees the moving frame moving to the right. The moving frame sees the stationary frame moving to the left. But they both agree on what that speed is. It's the same. You read about the Lorentz transformations. What are they good for? A is correct, and also B. They work both ways. The Lorentz transformation formulas allow you to go either from the moving frame to the stationary frame or from the stationary frame to the moving frame. And we're going to practice both of those today. So here's the basic moving frame pictures. This goes back to Galileo in the 1500s. If you have a starred point, a red star point, maybe it's just sitting there in the black frame, which is sitting still. And so it has a pretty simple formula for its motion. X is constant and time just runs and doesn't change anything. If you watch that red star from a frame moving to the right at speed v, though, Galileo said, look, in that frame, because it's moving, it looks like the red star is moving in the negative x direction. And so the primed x of that red star is equal to its unprimed x, its stationary x, minus vt. The red star is observed to move to the left, and the z's and the y's and the t's, they're all the same. They don't change. Galileo said this seemed obvious. It was obvious to him, and it was obvious to Isaac Newton. And it was wrong. Even though it seems obvious, it's wrong. Because you can't have the speed of light move at the same speed in all frames if you do it this way. You have to change it. And here's how it changes. Two parts are the same. The y coordinates and the z coordinates are the same between the two frames. At least we have that. In x, it's a little weird. It's got a piece of what we're used to. The prime frame x is x minus vt, but it's multiplied by this funny gamma factor. Notice that for ordinary speeds that Isaac Newton and Galileo would have been thinking about, and that even we use in the area of space travel, the v's we're talking about are way less than the speed of light. And so v squared over c squared is incredibly small, and gamma is basically 1 over 1, which is just 1. So in the limit of ordinary velocities, this is Galileo, but for rapid motions, things are different. You have this gamma factor. In time, it's even weirder. The t prime formula is not that t prime is equal to t, which would mean clocks run the same in both frames, which we know isn't true. The formula for t prime has a gamma in it, and it's also tangled up with x. It has a minus vx over c squared in it. Now, I'm sorry, but this is just the way the universe works. Where does this come from? Well, space and time have to transform this way between these moving frames in order to have the equations of electromagnetism look the same in all frames. We call these Maxwell's equations. You'll study them in Physics 220. Well, who cares whether the equations look the same? Maybe they're not the same in the two frames. Well, they have to be. The equations have to look the same, the equations of electromagnetism, that is. They have to look the same in all frames in order for the speed of light to be the same in all frames. And so we're stuck with this. Now, you might need to run these backwards. I gave you the formulas for x prime and t prime in terms of x and t. What if you want to know x and t in terms of x prime and t prime? Well, it's easy. The formulas are the same. You just switch the primes and the unprimed quantities and change the minuses to pluses, and it works exactly the same way. We're going to use both of these formulas to look at some problems. Okay, let's look at a friend from last time. This is the vertical light clock that you saw in that movie. So in this light clock, the pulse starts at x prime equals 0, and the clock is just going to sit at x prime equals 0 in its own frame. It's just going to sit at the origin. And the y prime starts at 0. The light pulse goes up to h at the top of the clock and then comes back down. That's the tick and the tock of the clock. And the time then goes from 0 in that frame. T prime goes from 0 to h over c to go up, and then another h over c to come down. And so the final time is 2h over c at the end of a tock. And we use primed coordinates because it's in the moving frame. Okay, so the events we're going to talk about, the Lorentz events, are when it starts at x prime equals 0 and t prime equals 0. When it returns at x prime equals 0, it's still at its same location in its own frame, but time is advanced in the prime frame. T prime is 2h over c. Now we want to find when and where do these events occur in the station frame. Well, we use these primed coordinates, put them in the Lorentz transformation equations, and see when and where these events happen in the stationary frame. Well, the first one's easy. Since both x prime and t prime are 0 for event 1, x and t, we'll call them x1 and t1 here, are also 0. For event 2, x2 looks kind of funny. x2 is 2h b over c squared. It's moved a little bit to the right, not very much for ordinary v's because it's got that 1 over c squared, but still it has moved. Galileo would have said that the distance it moved is 2h over v, because that's just vt, the time of tick-tock. But there's a gamma factor there, which makes things be funny, and we're not going to talk about that. The one we're interested in is the tick-tock time in the stationary frame. That's t2. That's the time it takes to go from t1 equals 0 to t2. That's a tick-tock. And it's gamma 2h over c. If you put t prime equals 2h over c in that equation, and then x prime equals 0. So what this says is that the time of a tick-tock in the stationary frame is gamma times 2h over c, but 2h over c is the tick-tock time in the stationary frame. Well, this is just time dilation. And this is where it actually comes from. Now, you might have thought, okay, you were fooling me by using a vertical light clock. If you have a light clock that goes in any other direction, it won't give you the same answer. So let's check it. Let's let the light pulse go bouncing back and forth along the x-axis. So at the beginning of the tick, x prime is 0. It's going to go over to x equal h in its own frame, and then the light pulse will come back to x prime equals 0. That's a tick-tock of the clock, and time advances from 0 to 2h over c during that time, because that's the time it takes the light pulse to go an h to the right, and then another h back to the left, 2h over c. And the clock is in the moving frame, so it has prime coordinates, and these are the coordinates. Well, where do these events occur in the stationary frame? Well, here they are. These actually look pretty familiar, right? This is exactly what we had for the vertical light clock. It's the same events. Even though the light clock is horizontal, it works the same way, and you get the same gamma 2h over c answer for the time of a tick-tock in the stationary frame. It takes longer, and it's time dilation. So it doesn't matter whether the clock is vertical or horizontal, you get the same answer either way. So it's not the orientation, it's the fact that it's a clock that makes it run slow. Let's see if we can find length contraction the same way. Let's look at a meter stick attached to the moving frame. So the right end of the meter stick is at x prime equals 0, is at x in the stationary frame. In the frame of the stick has its right edge at the origin, x prime equals 0, and it has its left edge at minus whatever its natural length is. And we're going to figure out what that is by doing this backwards. In the stationary frame, this is what it looks like. Event 1 is going to be when the right end of the stick arrives at the origin of the stationary frame. And we're going to let that happen at time t equals 0 and the stationary frame x equals 0. We now let some time run. The stick will move to the right, and the second event is when the left end of the stick is at x equals 0. The time it takes for it to get to that position is, of course, the distance L measured in the stationary frame divided by the speed of the stick, which is the same as the speed of the frame. So that's event 2, x equals 0 and t equals L over v. Let's see what this looks like in the prime moving frame. So here are the events. X equals 0, t equals 0 is event 1. Event 2 is when the back of the stick arrives. That's x equals 0 and t equals L over v. The Lorentz transformation we use is the one that goes the other way around. X prime is gamma x minus vt, and the time is the funny one. Let's see what these predict. So event 1 is just 0, 0, and if you put 0, 0 into the equations, you get 0, 0 out. So that happens at x prime equals 0, t prime equals 0. That's the right end of the stick in the stationary frame, sitting at the origin in the stationary frame of coordinates. Event 2, let's just look at the x prime. We're focusing on position here and not time. The x prime of the second event is gamma, and then 0 because the x is 0 in the stationary frame, and v L over v, well, the v's cancel, and you just get minus gamma L. Well, this is the fixed x position of the left end of the stick. The stick is apparently gamma L long. So its own length, gamma L, is longer in its own frame than the length L measured in the stationary frame. So it's shorter in the stationary frame, and this is called length contraction. Moving sticks are short. All right, so now let's do something really fun. You've just learned about relativity, and you get the bright idea of running toward a barn, carrying a pole that is longer than the barn, and you reason that someone watching from the Earth frame will see your pole be short. If you run fast enough, close enough to the speed of light, this long pole that's longer than the barn will be length contracted so that it's short enough to fit inside the barn. But wait a minute. If you look at this from the frame of the runner, the guy carrying the stick, the pole, the barn is moving and it's short. And so now you have a long pole and a short barn, and it can't possibly fit. But from one frame it fits, and from the other frame it doesn't fit, and that makes no sense. That sounds like a paradox. If that were true, we would say the whole thing is a crock, and that would be good news. You wouldn't have to learn it. But something very odd happens when you actually analyze this using events with the Lorentz transformation. So let's turn this into an event picture. These are the events as observed in the stationary frame. You have a long barn. A pole goes by at very high speed. Its length is contracted, and we can tell that it fits in the barn because we define two events. Event one is when the left edge of the stick lines up with the left edge of the barn. Event two is when the right edge of the pole lines up with the right edge of the barn. And those are simultaneous events because the pole fits. So they both occur at t equals 0. But the one on the left occurs at x equals 0, and the one on the right occurs at x equals L, where L is the length of the barn. So those are the position and times in the stationary frame, and they're simultaneous in the stationary frame. We built them that way. Let's see what they look like in the moving frame of the pole. So we have to use these little red Lorentz transformation equations up there in the upper right-hand corner. That will tell us what the primed coordinates are as we analyze these two events. So here's event one. That's left edge of the pole is at the left edge of the barn. Well, x and t are 0 there, so if you put those into the Lorentz transformation equation, you get x prime equals 0 and t prime equals 0. All right, that looks pretty natural. The back of the pole event, this is the right edge lining up with the right edge of the barn event. If you use the Lorentz transformation equations on that, you find that the x prime, where that occurs, is gamma L, and the time at which it occurs is minus gamma VL over c squared. That's a negative time. That means that the primed times of these two events, t prime 1 is 0 and t prime for the second one is actually earlier in time. It's a negative time. It happened before the left edge of the pole hit the left edge of the barn. What the heck does this mean? Well, it means that events that are simultaneous in one frame are not simultaneous in another. You saw that in the video last time. The formulas, the Lorentz transformation formulas, predict this. Here's what happens in the frame of the pole. In the frame of the pole, you have a short barn. It's moving not in the x direction, but in the minus x direction because you had the pole moving in the x direction. Event 1 is when the short barn, left edge of the short barn, touches the left edge of the pole. The events mean what they mean. They mean that left edges touch left edges. You don't change that. You just change the positions where they happen. Notice that if the barn is moving to the left, the time at which the right end of the barn and the right end of the stick were together must have been earlier in time. Like this. Well, you can't see for the inset. I will publish versions of these slides that have me removed so you can see what's on all the slides. I tried to make this one better, but I failed on this one. So they're not simultaneous, and the way you get the long pole to fit in the short barn is to have the two events when the pole ends and the barn ends touch be at different times. It's all perfectly consistent. Event 2 happens first. So let me see what you learned from that. The resolution of the pole barn paradox is that, which of these? And the answer is B. Simultaneous events in one frame are not simultaneous in another frame that's moving with respect to the first. Well, here's another idea that's in the book. This is something else that seemed obvious to Galileo and Newton. Suppose you're on a bus, and the bus is moving at 20 miles an hour down the street, and you wind up at the back of the bus, and you throw a ball at 30 miles an hour down the length of the bus. For an observer outside, they see the ball moving at 50 miles an hour, 20 miles an hour worth of bus velocity, and 30 miles an hour of you throwing the ball relative to the bus. This just seems obvious. It's wrong. The correct formula for this would be that the combined velocity seen from outside is the 20 miles an hour in the bus plus 30 miles an hour that you threw divided by 1 plus 20 miles an hour times 30 miles an hour divided by the speed of light, 186,000 miles an hour squared in the bottom. Well, you know, that's essentially 0. And so for low speeds, the formula you like works just fine. But for high speeds, it doesn't. Notice that I've left plus minus in this equation. You need to know which one of those to pick. The plus minus in the top and the plus minus in the bottom are linked. That means if you pick plus in the top, you have to pick plus in the bottom. If you use minus in the top, use minus in the bottom. And the way you remember which one to use is that if the velocities are such that they add so that you get extra velocity in the top, then you use the plus sign. If you stand in the back of the bus and you throw the ball the other way so that the velocities subtract, you'd use a minus. And this formula, as odd as it looks, it's the one that agrees with experiments. So here's an example. Suppose a spaceship travels by at 0.8 c, and someone on the ship fires a bullet in the direction of travel at 0.9 c, and you're watching this happen from the stationary frame outside. At what speed do you see the bullet go by? You should get your calculator out, you know, one of these things. Get it out and put the numbers in. So in the top, you'll have 0.8 c and 0.9 c. That's 1.7 c in the top. It looks like you've made it go faster than the speed of light, but you have a denominator to put in. And when you put in 1 plus 0.8 times 0.9, and the c's cancel, you get 1.72 in the bottom. So you have 1.7 in the top, 1.72 in the bottom, and the answer turns out to be D. It's 0.99 c. In fact, I think there's actually another 9 in there if you work it out. So it comes very close to the speed of light, but it can't go past it. Here's another example of that idea that nothing can go faster than the speed of light. Imagine two airplanes moving apart from each other. Each one is moving at 1.5 times the speed of sound with respect to the stationary Earth below. If one of them sends a sound pulse to the other, will the sound pulse be received by the other airplane? I'll give you a minute to think about this. Two supersonic jets flying apart from each other, each one moving at 1.5 times the speed of sound with respect to the Earth. Well, the answer is no. They will not. The pulse will not be received because the first airplane sends out a sound pulse. That pulse travels at the speed of sound through the air, but the other airplane is going 50% faster than that away from the sound pulse, and so it will never catch up. Just can't get there. Now let's do it with spaceships. Of course, I'm not going to let the spaceships move at 1.5 times the speed of light. You can't do that. We don't know how to make anything go faster than the speed of light. So we'll let them be at 3/4 of the speed of light. That's pretty fast. Their relative speed, if one's going 3/4 to the right and the other one's going 3/4 to the left, that's 1.5. Their relative speed with respect to each other in the frame of the Earth is 1.5 times the speed of light. Now, there's nothing physical moving at that speed, but I could say, okay, well, one's going to the right at 3/4, the other one to the left at 3/4. That looks like 1.5. The other one sends a light pulse toward the other. Will the light pulse be received? And the answer, of course, is yes, it will be, because you have these two spaceships. They're moving apart from each other at what looks like 1.5 times the speed of light. But as soon as the one on the left sends the light pulse out, it's moving at c, and the other ship is only moving at 3/4 c, and so the light pulse will catch up. You can't do the thing that the airplanes can do, which is run away from a sound pulse. You can't run away from a light pulse. There's no way you can run away from a light pulse. It will always catch you because you cannot move faster than it can. I want you now to pause the video, go to YouTube, look up Mechanical Universe, Chapter 43, start at 18 minutes and 54 seconds in, and watch 7.5 minutes of video. This is the twin paradox. Okay, so you've come back from watching the video. Why is it a paradox that one of them is moving and thinks the other one's clock is slow, and the other way around, they think the same thing? Why is this not a paradox? So let's see what you learned from that. The resolution of the twin paradox is that one of these is the right answer. It's C. They actually didn't have the same experience. It's really only a paradox if they both experienced the same thing, and then they both measure each one to be, the other twin to be older than they are. That's a paradox if the same thing happened to both of them. But the same thing didn't happen to both of them. The one who stayed home didn't feel any violent accelerations. The one who travels does. He is non-inertial, meaning he feels huge acceleration forces. When he blasts off from Earth, he's smashed down into his seat in the rocket ship, and the other twin doesn't feel anything like that. And then he has to slow down at the other place, feels those gravity forces of acceleration again, and then coming back, he feels them 2 more times. And this makes all the difference. It breaks the symmetry of the paradox. And so there is no paradox. The guy who moved fast to another star in a spaceship actually does come back younger. Okay, here's some questions from next time. You have some reading to do, and you have some homework this time. And I will see you on Wednesday.